This video will explore the fascinating world of fluids, covering key concepts such as states of matter, density, pressure, and important principles like Pascal's and Archimedes. We will also look at phase changes, viscosity, and surface tension. Matter exists in 4 states: solid, liquid, gas, and plasma. Solids have a definite volume and shape, with molecules in a rigid structure. Liquids have a definite volume, but no definite shape. Gases are easily compressed and lack definite shape or volume. Plasma is an ionized gas, the most common form of matter in the universe. Phase changes include evaporation, condensation, melting, freezing, and sublimation. A volatile liquid, like water, evaporates quickly. Sublimation is the direct change from solid to gas, as seen with dry ice or with comets near the sun. The term fluid refers to both gases and liquids, as their atoms or molecules are free to move around, unlike those in solids. Fluids can flow. As a fluid gets hotter, its molecules move faster, causing the fluid to occupy more space. Density, symbolized by ρ, is defined as mass per unit volume, or m/v. The SI unit for density is kilograms per cubic meter. For example, the density of water is about 1 gram per milliliter. Pressure, P, is defined as force per unit area, or F/A. The SI unit for pressure is the Pascal, equivalent to 1 Newton per square meter. Atmospheric pressure at sea level is approximately 1 atmosphere, or 101,000 pascals. This example shows how pressure depends on the area over which a force is distributed. A 6-pound book exerts different pressures depending on its orientation on the table. Note that all these calculated pressures are very small compared to atmospheric pressure. Unlike a book resting on a table, the pressure in a fluid acts in all directions. The air exerts thousands of pounds of force on a desk, but the air underneath pushes up with the same force. We are not crushed by the atmosphere because internal and external pressures are balanced. The pressure at a given depth in a fluid is uniform and acts everywhere. Snowshoes prevent sinking because they increase the area, decreasing pressure. Swimmers float better in the ocean because salt makes seawater denser. A long snorkel won't let you dive deeper because the surrounding water pressure would collapse your lungs. On average, Earth is denser than the sun, but the sun's core is much denser than anything on Earth. For most liquids, increasing pressure increases the freezing point, as high pressure forces molecules closer together to form a solid crystal. Water is an exception. It expands upon freezing. Therefore, squeezing water makes it harder to freeze. Pressure from a skater on ice can actually cause a small amount of melting. Lower pressure makes it easier for a liquid to boil, meaning increasing pressure raises the boiling point. In the mountains, water boils below 100 degrees Celsius due to lower air pressure. In a pressure cooker, the high pressure allows water to remain liquid and hotter, cooking food faster. The freezing point of a solution, like salt water, is lower than that of the pure solvent. This is because solute molecules interfere with the solvent molecules trying to form a crystalline structure. A higher solute concentration causes a greater reduction in the freezing point. Adding salt to water actually increases its boiling point. The dissolved ions reduce the water's vapor pressure. To boil, the vapor pressure must match the air pressure, meaning salt water needs to be hotter than 100 degrees Celsius to boil. Suction is a force that draws a fluid or solid by an external-internal pressure difference. A vacuum cleaner works by creating a low-pressure region inside, causing the higher external air pressure to rush in, carrying dirt. A suction cup sticks to a wall because the greater outside pressure forces it against the surface. Pressure depends on fluid density and depth, given by the formula P equals $ρ$gh. The pressure at the bottom of a container is due to the weight of the fluid column above it. Total pressure includes atmospheric pressure on the surface, making the complete formula $text P equals text P underscore text A plus ρ text gh$. Pressure depends on the depth of the fluid, not the container's shape, provided the height is the same. Therefore, the pressure at the bottom of all these containers is the same, regardless of their varying shapes. This principle applies to the pressure within the fluid. At a given depth, the pressure in a fluid must be constant. If there were a pressure difference at the same depth, the fluid would be moving, which contradicts the state of fluid equilibrium. The pressure difference between the surface and a depth h is $ρ$gh, where $ρ$ is the fluid density. Since points Q, Y, and Z are at the same depth, the pressure at Z is the same as the pressure at Q, despite the different container shapes. Barometers measure air pressure using a column of mercury. The pressure at points A and B, at the surface of the mercury pool, is the air pressure. The pressure difference between B and C, where C is a vacuum, is $rho$gh, which equals the air pressure. Pascal's principle states that any change in pressure applied to an incompressible fluid in a container is transmitted undiminished throughout the fluid and to the container walls. Squeezing toothpaste or performing the Heimlich maneuver are everyday examples of this principle. A hydraulic press uses Pascal's principle. A small force F1 applied to area A1 creates pressure that is transmitted to area A2, resulting in a larger force F2, lifting a heavy object. The output force is magnified by the ratio of the areas, A2 over A1. The work input and work output in a hydraulic press are ideally equal. The volume of oil displaced is conserved. A1H1 equals A2H2. This leads to the relationship F2H2 equals F1H1, consistent with the conservation of energy. We see objects floating in fluids based on density. Even dense objects like steel in an aircraft carrier can float. This phenomenon, and why objects appear lighter underwater, is explained by the work of Archimedes. Archimedes' principle states that the buoyant force, Fb, on a submerged object equals the weight of the fluid it displaces. For objects of the same volume, the buoyant force is the same. An object sinks if its weight is greater than the buoyant force and floats if its weight I-less. When an object floats, the buoyant force equals its weight. A floating boat displaces a volume of water whose weight is equal to the weight of the entire boat. More load means more displacement, causing the boat to ride lower. Submarines and blimps both rely on Archimedes' principle. A submarine displaces water and a blimp displaces air. For both, the buoyant force must balance the vessel's weight to achieve neutral buoyancy or flotation. The proof of Archimedes' principle involves pressure. The buoyant force is the difference between the upward force, Fup, at the bottom, and the downward force, Phi down, at the top. This results in $text F underscore. Ext B equals Shiro text GV$, which is the weight of the displaced fluid. The ice sculpture of Poseidon floats because ice is less dense than water. The fraction of the statue submerged is equal to the ratio of ice density to water density. For this sculpture, 8.3% of the volume will be above the water. Only about 1/8 of an iceberg is typically above the waterline. The compacted ice in the core is denser, keeping most of the iceberg submerged. If the less dense snow layers are lost, a smaller fraction of the iceberg will appear above the surface. If Bugs Bunny pours out water while standing on a scale, his apparent weight increases. This is because less water means less displaced volume, resulting in a smaller buoyant force and a larger normal force read by the scale. For an incompressible fluid, like water, flowing through a pipe, the volume of fluid passing through any cross-section per unit time must be constant. This means the product of the cross-sectional area and the fluid speed remains constant. A times versus equals a constant. Therefore, a wider pipe section results in slower fluid speed. The Bernoulli equation describes the relationship between pressure, speed, and height for a non-viscous, incompressible fluid. P plus 1/2 rho v squared plus rho gy equals a constant. As the fluid flows, these quantities change, but their sum remains constant throughout the pipe. Here, P is pressure, rho is density, v is fluid speed, and y is height. The Bernoulli equation can be derived using the work-energy theorem. The net work done by the pressure difference is P1 minus P2 times V. This work changes the potential and kinetic energy of the fluid volume. Setting the work done equal to the change in potential and kinetic energy. P1 minus P2 times V equals the change in potential energy plus the change in kinetic energy. Dividing by volume 5 and rearranging the terms leads directly to the Bernoulli equation. The final form of the equation, P1 plus 1/2 RHO version 1 squared plus RHO GY1 equals P2 plus 1/2 RHO version 2 squared plus RHO GY2, proves that P plus 1/2 ROV squared plus RHO GY is constant throughout the pipe. This equation is crucial in fields like aviation and medicine. Bernoulli's principle states that the faster a fluid moves, the less pressure it exerts. This is a special case of the Bernoulli equation for constant height, where P plus 1/2 RHO V squared equals a constant. Thus, if fluid speed increases, pressure must decrease. The Bernoulli principle helps explain airplane lift. Air flowing over the curved top surface of a wing travels faster than the air underneath, resulting in lower pressure above the wing, which creates an upward force. This lift, combined with the downward push of air, allows the plane to fly. Consider an example of water flowing in a horizontal pipe. Since the pipe widens, the speed decreases from 8 meters per second to 2 meters per second. Using the constant height Bernoulli equation, we calculate the pressure difference. The change in pressure is 30,000 pascals. In this setup, air flows faster in the constricted section of the upper pipe, resulting in lower pressure. This lower pressure allows the water level in the middle vertical tube to rise higher than the others. The pressure difference is determined by the height of the water column. $delta $P equals $rho $GH. To determine how far water lands from the base of the tower, we use the Bernoulli equation, assuming the pressure at the top and the hole is the same air pressure. We also assume the speed at the top is negligible due to the large area. Starting with the simplified Bernoulli equation, $8 rho $G equals $1/2 rho $VH squared, we find the speed of the water leaking from the hole, VH, is the square root of 2GH. For this example, VH is approximately 12.522 meters per second. This relationship is known as Torricelli's principle. The water molecules exiting the hole are projectiles launched horizontally from a height of 15 meters at 12.522 meters per second. Using projectile motion equations, the time of flight is 1.75 seconds. The horizontal range is then calculated as speed multiplied by time, which is 21.9 meters. Bernoulli's principle is relevant to heart attacks. When plaque narrows an artery, blood must flow faster around it, creating a low-pressure area. The pressure difference between the normal and constricted sections can dislodge the plaque, which may then block a smaller artery, leading to a heart attack. Strong winds blowing over a flat roof move faster, creating a low-pressure region above the roof. The air inside the house remains at normal atmospheric pressure. This pressure difference, high inside and low outside, can generate a significant upward force, potentially lifting the roof off the structure. Viscosity measures a fluid's resistance to flow. High-viscosity fluids flow less easily, like molasses compared to oil. In a pipe, fluid layers shear against each other due to internal friction, with the fastest flow in the center and zero speed at the walls. The Bernoulli equation is applicable to fluids with negligible viscosity.